again, welcome to Matplotlib for publication, presented on behalf of Lund University and as part of the NAISS training program. The lecture will consist of the lecture blocks will consist of three main parts: the basics of Matplotlib, the formatting and accessibility for the print medium, and a third part. The last lecture block will be sort of a grab bag of tips and gotchas when using Matplotlib. So I realize some of this will, for some of you, this will be review, but I know for a few of you, this is a new package. So Matplotlib is the standard library for visualizing data in print, and it's the standard Python library for visualizing data for print or digital medium. You can have static figures, interactive and animated figures, which I won't go into today, and you can embed figures in a Jupyter notebook, which we will do, and you will see. You can have 2D plots, 3D plots, single tiled, Cartesian, polar, any number of other coordinate systems are supported, and there's excellent documentation with lots and lots of tutorials and lots of examples. To make sure that everybody is on the same page as to the basic terminology, this is a nice anatomy of a figure plot that is actually part of the introduction section of the official documentation. So the main thing I want you to understand is the difference between a figure and an axis object. So the figure is this entire thing, the frame, and everything in it, all the white space, all the plots, all the different axes instance. And an axis instance is one pair or one triple of axes. So an X and Y pair. An X and Y pair for a 2D plot and an XYZ triple for a 3D plot. And there can be multiple axes instances on the same figure. You also need to be familiar with a couple of Python terms. That is args, which stands for positional arguments. These are usually mandatory. And then there are quargs, which stands for keyword arguments. And these are usually optional. These are the ones that where you have to type the name of the variable and equal sign and then put in a value. You'll see quargs a lot in this presentation. So that's why I wanted to make sure that everybody knew what those meant. When we refer to markers, we refer to the shapes that are used to indicate individual data points. A line and curve will be used interchangeably, but basically it means a smooth function of many points arranged in a line. Also, you should also be aware of the term ticks. That refers to the little increment marks on each axis. So there will be tick labels and there will be axis labels. The tick labels are the numbers or whatever other increment is being used on an axis, and the axis labels are actually the titles of the axes. I'm not going to use the term spine much, but a spine is basically the long line that the ticks stick off of on an axis. You'll also see grid lines a little bit, but those hopefully are a little bit more self-explanatory. And then, of course, where you have markers and lines indicated as little sort of line segments or example markers with the label of a curve next to it, that's the legend. All right, now I know a few of you are on different facilities, but this is geared towards Lunark users, but there will be some similarities between Lunark and other facilities. So on the Lunark HPC desktop, and I'll show you this in a couple of minutes, the recommended usage for for running Python is to go to Applications, find this Applications Python option, and then go to either Jupyter Lab or Anaconda 3 Spider. Both of these default to the latest Anaconda 3 version, but you can change that under the job settings option, which you'll see in a minute. Both of those are currently running Python 3.11.7. The exercises were written with Python 3.11.5, so it basically, you're golden if you use 3.11. 3.10 to 3.12 are probably all acceptable. I didn't necessarily get a chance to test everything, but there's the functions that I used. I stayed away from the ones that were unstable. Now, this is not as recommended, but on other facilities and also at Lunark, you can run Matplotlib from the command line or from a Slurm script. I imagine for those of you who are at a computing center that does not have desktop on-demand applications, this will be the standard way that you run it. So you will need to load the modules that contain what you need. For at least on Lunark, or at least on Cosmos, if you load Anaconda 3, you will have everything that you need. It includes NumPy, Matplotlib, SciPy, Pandas, all sorts of things. But you have to be a little bit careful when creating Anaconda environments, because they can mess with your bash RC. If you use PyP distributions, then the version of the GCC compiler that you need determines what version of Python you can load, and therefore what version of Matplotlib you can load. So basically it comes down to what version of Matplotlib you want depends on what version of Python that you need, which depends on the version of GCC that you need. So you can use module spider, and then whatever dependency sort of fixes your or determines your, so whatever dependency determines everything else in your code. Just use module spider and the name of that dependency to check what GCC requirements or what Python requirements are required for you. And then you can load ML GCC, and then at least on Lunark, if you then just type in ML Matplotlib, all of the other dependencies, including Python, SciPy bundle, and all of that stuff, get loaded for you. But that may be different on other module systems. They vary. On other computing systems, the names of the modules and what are available varies a little bit, especially in terms of the names of the precise names of the modules and whether they're uppercase or lowercase. On Lunark, I should warn you, right now, Matplotlib 3.9.2 is having some kind of malfunction, so you don't want to use that one. That's just for the very newest GCC version, so everything before that should work. And now I will go ahead and start sharing a example with the Lunark on-demand desktop system. So let me share the other screen, which is my ThinLink client. All right, right now you should see a scripter. I'm going to minimize that for the moment. And minimize, well, that's not what I was trying to do. All right, so what you can see before you now is the Cosmos, the Lunark HPC desktop on Cosmos. So if you want to go to the the process I use to open Spider is to, and actually I will just, I will close this and show you. That way I can get back some of this. So just go to Python, Spider, and then what comes up is this little GFX launcher pop-up. And here is where you can set the number of the wall time you need, the project or account that you need. For you, for Lunark users, it will be LU 2025-7-37. I'm using the teacher account, so I'm going to use this one. 1 task per node is fine. We're not doing anything intensive today. Most of the time, 1 task per node is fine. If you need to change anything, you go here to resource specifications, where you can change the job name, task per node, memory specifications, all of that stuff. So then I just click start. And this process is pretty much the same for Jupyter Lab. And now the scripter is back. To show you how this works on in the terminal, and I should advise that this terminal right here is running on the front end, so you don't want to use this for anything intensive. But for here, it's just for showing the module structure, it's fine. So I'm going to do ML Spider Python 3.11.5. All right, and what that shows me is that it needs to load, I need to load GCC Core 3.2.0. So let's say I'm just saying that, I'm just using as a demonstration that if you wanted to use this specific version of Python, this is how you would find what it depends on. And then if I quit and, no, go away. And if I quit, and then what I can do is load GCC. I always just load GCC instead of GCC Core. They're not quite interchangeable, but close enough. And then I can actually, if I'm sure that everything in here is correct, I can just load everything all at once, like that. And actually, if you load one thing that determines the versions of everything else, and there's only one specific version of a particular package associated with one of these prerequisites, then you don't have to include the version number. So then now I can show you what all that loaded, and it's quite a bit. So it's 49 modules, and then this is the version of Matplotlib that got loaded. Now there's one other little gotcha here, and that is that if you are working at the command line, or if you're working in a script and you're running a script like so let me cd documents. It's not my usual keyboard. So I've got this demo plot function that I've loaded. That that is a copy of the little code along exercises that you'll be using shortly. If I wanted to execute this, I would write something like Python demo plot 1.py. And if I try to run it as is, it does not have an interactive backend or display, which is the display function that's required. So typically at the command line, what you would need to do is, or for execution at the command line, what you need to do is include the lines, import matplotlib, I usually use as MPL for short, and then set matplotlib.use, and then in parentheses put this tk-ag. This is the one that's most reliably used at most of the facilities that I've tested this on. There are some facilities and in some circumstances where if you have PyQt5 loaded, you'll instead want to use this Qt5 ag. But and that's also the one that's compatible with Spider 3, but you don't typically need to specify it if you're running in Spider like this. So let us now return to the presentation and share my screen again. All right, again, so this is the project name that you need if you're on Cosmos. Come on, there we go. So the very first thing that you do whenever you import whenever you start a Python code is you import pyplot. Sorry, anytime you are writing a Python code to use Matplotlib, the very first thing you're going to import is matplotlib.pyplot. And the standard call is from Matplotlib import pyplot as PLT. And this provides you with sort of MATLAB-like functions to create or alter plots and their components. In older code, you may see PyLab. That's about 10 or 15 years out of date now, though, so hopefully most mentions of that have been expunged, but if you see it, try not to use it. Also, if you decide that you want to do the coding in Jupyter, what you will need to do after the standard import is include this %sign matplotlib inline. Here are a couple of minimal working examples. There are two application interfaces with that you can use. There's the single data series. There's the implicit application programming interface, or API, which is appropriate for single data series, no typesetting, just really quick. I got to look at this to see if my data is correct, or to see if my data has anything funky going on. That's what you use the implicit interface for. It's very simple stuff like this. So you can just do plot.plot, your X data, your Y data, and then this little format code. Here you can include a single letter. In this little format string, you can include a single letter color specifier, a line specifier, and or a marker specifier. If you include a marker specifier with no line, it doesn't show any lines. If you include a line with no markers, it shows a line without markers. And if you show a line, or if you use all three parts of the format string, then it will show a line with markers on it. I'm going into that. Now there's also the explicit API. This is more appropriate if you need to do typesetting or include subplots or add other features to a more polished plot. So this is typically the one that you will want to use. So for this, you have to sort of explicitly instantiate a figure and an axis object separately. And here, X can actually be a single set of axes, or it can be an iterable of multiple axes objects. And then you can include, and you almost always use this plot.subplots command, even if you only have one plot. Then, of course, once you have instantiated it, then most of the plotting commands are called off of this ax object. So you put plot, or ax.plot, ax.set x label, ax.set y label. So formatting commands like the setting the labels and the titles and all of that stuff. In the explicit interface, it usually has the set underscore in front of the command that in the implicit interface is just like it's just dot X label or dot Y label. But plot.show is the same for both. And the figure instance can sometimes be used for things like Colorbars. Come on. All right, now we're going to do I'm going to give you guys a few minutes head start to try your own little coding program. So for this x equals numpy.linspace -5 to 5 for 50 points. So you'll need to import numpy as well. On the same axis object, you will plot cosine as a solid blue line and 1 over parentheses 1 minus exponential of x as a red dashed line. And use the explicit API. If you're in Spider, the default option is for it to display here in this upper right corner under this Plots tab. But you can change that by to the pop-out GUI that I prefer by going to Tools, Preferences, and then you scroll down to, I'm trying to remember, I think it's IPython console. Yes, IPython console, and then go over to Graphics. And then usually the inline usually it defaults to saying the inline backend is selected. What you want to select instead is automatic. And you can also adjust the default resolution and default sizes here as well. So then if you changed anything, click apply. Otherwise, click OK. Now that now you can see the solution here. I needed to import NumPy, obviously, in order to make the x-axis plot and to use the cosine and exponential functions. Then I used Matplotlib import. I'm going to comment that back out since I don't need it in Spider. Then there's the x assignment, fig ax, plot.subplots, didn't need any quarks this time. Then ax.plot, x, the function, and then this is the blue curve. Sorry, I haven't asked for labels yet, but you'll see them in a second. So then for a blue solid line, it was a B and a single dash. For a red dash line, it's a red and an R and 2 dashes. Then it's just ax.set x label, ax.set y label, and then strings for the 2 titles. Legend has not been included yet, so I'll comment that out. And you'll see that in a second. Your results should look like this, more or less. I already went over set X label and set Y label. You can also set title. Now, if there are multiple subplots, this set title applies to a specific subplot. To set the title for the entire figure, you have to do set subtitle. So there's a set underscore and then SUP. P is in, I forget the Patrick. Let's say that. P is in Patrick and then title, just like it says here. For the implicit API, it's just plot.x label, plot.y label, and plot.title. And then there's the to title an entire figure, it's fig.subtitle. Then most plotting functions include a label kwarg, and that lets you pass that string to legend and then put a legend on the plot. And then you control the legend position with this lock command. within the plot area, or a B box to anchor, which allows you to set the legend outside of the plot area. Some plotting functions like bar take an array of labels as a first argument, and then so you don't need to include a legend. And you can also explicitly pass lines or data handles for instance, if you have multiple sets of contours on the same plot. That's what's called making a proxy artist. We'll go into that a little bit much later in this presentation program. I think it's either the second or third lecture. Now, if you want to place your text, your legends or other text elements, there are a couple of other things you need to know. So text is the base function. It only adds and formats text. And there's also an annotate function, which adds not just text to a plot, but also connectors like arrows from the points to the text. And the positions for both of these are controlled by this ax.trans axis. Or, well, the positions for both are in data coordinates are by default, unless you set the axis transformation to ax.trans axis. That switches the coordinates to axis relative coordinates, where the x and y axes are unit length and 0, 0 is the bottom left corner. Now, to be clear, it's the bottom left corner of the axes, not the entire figure. So if you see negative numbers, that means it's either below or to the left of the axis object. This is also the way that you use B-box to anchor in the legend placement to place the legend outside of the plot. More often, you'll be using this lock quarg instead, where you can set it to either an integer or a two-word string like lower left or upper center or upper right or just center if you're crazy enough to stick it right smack in the middle of the plot. You can also make whole figure legends, where then you can include this outside word, and then upper center or lower left or whatever vertical alignment and horizontal alignment term that you want to use. Now you're going to try and add the labels to your x and y axes and label the curves. So I want you to label the blue solid curve A for now, and the red dash curve B. And then for the x and y axes, you can title them just x and y. I have them capitals. I don't really care if you use capitals or lowercase. Now, it is possible in the plotting command to plot multiple sets of lines if you don't, in one plotting command, if you don't include the labels. Once you include labels, then you have to split them up into separate plot commands. Hopefully nobody did that, but let me see. Yes, the axes are the part in this. Can you see my cursor? Just somebody scream out yes or no if you can see my cursor.
Yes.
Cool. All right, so the axes parts are just inside of this this black frame here. So it's the x and y axes, their boundaries, and anything inside of them. And the figure is the entire thing, including the axis titles, figure titles, and all of that stuff. The whole shebang. All right, so I had already included the axis labels, but I will just add the print labels back. So I'm just labeling that A, and then this one was A equals B. Oops, sorry, this is not my my usual keyboard. Now I have decided to put the legend in the lower center. So now if I plot that, it looks like that. You can also adjust the axis scales. There's a linear option, log option, logit, simlog, which is similar to log, except it extends the log scale into the negative range. And then there's a function. There's a function set, and this one, if the scale argument is function, you have to define both the forward and reverse transformations, and pass each of those functions as a tuple of function names. So some of the plotting functions have x scale and y scale quarks, and for others you'll have to set x dot set x scale or x dot set y scale. But for any of the titles of these functions that you see here on the right are available as options, except for Mercator here. Mercator is an example of a function that was defined in forward and reverse in the examples, or in the documentation. Now, usually automatic tick spacing is fine, but sometimes, like if you're using a log scale and you have and your data span more than, I think the range is 7 or 8 decades. If you have more than those, you may have to do some extra finagling to show minor ticks again, or to show single decades instead of every second decade. I've included a link to some more examples if you need help with this. We'll go into, you'll get some practice with this in the exercise block. Now, subplots. These are super handy. You'll be using this a lot. If you create an axis objects with the plot.subplots command, then you can make an iterable out of it. So you can choose whether to define axes as a single object and then index it, or you can also substitute where this code snippet has axes, you can instead put a tuple and define like x1, x2, and so on and so forth. And then you don't have to include indices. But I find indices more handy because then you can iterate over them, and that allows you to set the same commands for every. For instance, if you have the same x and y axis labels on this on every plot, then you can iterate over them and set them all at the same time in one go, or only set the ones that are along the outside edge with a modulo operator like this. So this code snippet here is an example of how you might iterate over an axis object to only set the labels for around the outside edges. There's also a plot.subplot singular. This is more tedious to use, but there is one use case for it, and that is if you have separate projections for each plot. For example, let's say I had a trig function that I wanted to show in both Cartesian coordinates and polar coordinates. So I can define figure equals plot.figure, and then add subplots to it one at a time. So I have this plot.subplot, and then this number code here that the first 2 digits are the numbers of rows and columns total, and then the last digits is the number, is like an index number for that individual plot. And in this notation, it only goes up to 9. But if you use the in rows and in cols quargs, then you can have more than 9 subplots total. So here I put the here I've plotted the x and y axes singularly and in a polar coordinates. So now there's a third option for subplots, and that's subplot mosaics. And these are really handy if you need a plot to span multiple rows or columns of a subplot grid. So I picked a really complicated layout so that just to show you all the different details. So the layout at right is rendered over here in as a string, where there's two ways of specifying it. You can specify it like a comment string, where then you can sort of lay out the rows and columns visually. So here I'm saying that object A spans two rows, but one column. Subfigure B spans two columns and only one row. Subfigure C sits right in the middle and occupies only one row and one column. Then there's a dot for an empty space, and then this D figure that spans the entire bottom row. Now it's important to realize that if you have subplots defined this way, you can only use a single character as the dictionary key for each plot, but then you have the opportunity to use those single characters as dictionary keys that then you can use to set various subplot quarks with. And then you can use this per subplot quark command, where you have a dictionary, and then each plot has its own key, and then you can assign each of those their own little nested dictionaries, where you can set things like the projection and the X scale and all of that stuff. And what's nice about this is that you can also assign the same parameters to multiple plots at once if you give the dictionary keys as a tuple. I won't have any examples on this, but this is there so that you know this exists, because this does not come up a lot. And so sometimes it's hard to find. Colorbars, you'll also use this a lot. Colorbars are methods of figure, not axes. And this is so that you can apply a color bar to an entire figure instead of just a single axis. Or you can put it on its own, axis. And that's something you can do if you need some more complicated formatting, but we're not going to go into that this time. So axis objects must be passed to Colobar explicitly, and the first argument must be something called a mappable, which in this case is pretty much always a plot. And so for these, you have to set the if you're plotting something with like ax.plot or ax.mshow, you have to assign that to a variable name and then pass that variable to the as the first argument to fig.colorbar. But that is only if you have more than one subplot. If there's only one plot in your figure, then you can essentially just have fig.colorbar and empty parentheses if all you need is the default settings. For everything else, you need a lot of these little subquarks, a lot of these quarks. So then there's this ax quark, and that allows you to associate the color bar to a particular axis. And that basically tells Colobar which axis to steal space from. Then there's an extend quark, and that lets you set whether either of these two endpoints are pointed instead of squared off. And then there's an orientation quark that lets you choose whether the the color bar is plotted along the right or along the bottom. And there's also a shrink quag, which is very handy for the vertical orientation, because I find that if you use the default size, it's almost always too long. So for this little example at the right, I actually had to shrink the color bar on the bottom by 50% in order to make it the same height as the figure. But anyway, also pay attention to this little .mshow command. So all this is just a way to render a 2D array of values as an image. You can pick color maps, normalizations, and all of that stuff. And I'm pointing that out because the next example in a couple of minutes is an mshow figure. Now, the last thing before we go to the final little demo code is to talk about figure output formats. The default figure size is 6.4 inches by 4.8 inches, or about 16 by 12 centimeters. And the default resolution in most GUIs is 100 dpi, unless you're in Jupyter Lab, which has a default of 80 dpi, and that's just nowhere near enough. So you can adjust the figure size, resolution, and aspect ratio with the DPI and fig size quarks. So DPI controls the resolution. Fig size controls both the size and the aspect ratio. And those are quarks of figure, subplots, savefig, and msave. So if you set those arguments in figure or subplots, they're set at runtime, and then if you save it at the GUI, they're preserved that way. If for some reason you only want those parameters in the save version of the image, like for instance, if you are not even going to show the plot because you're producing this figure automatically, then you can set DPI and fig size inside of savefig or msave. msave is specifically for RGBA images. I've never used it. Most of you probably won't use msave either. So the one you probably have to remember is savefig. For journals, the recommended output format, or at least the format that I recommend, is PDF. A lot of journals will recommend EPS as their preferred format, but those require special viewers, and they often don't support transparency. The default format is PNG, but that's large in memory, so it's advised that you don't use that. JPEG is sometimes also accepted, and it's very efficient in memory, but it's lossy, so don't edit it once you've made it. And then, let me check. Oh, SVG format. Let me briefly go back. Oops. So there, I saw a question about SVG format. That is available with extra modules. I believe the documentation on savefig points you to the modules that you'll need to load if you want to save images in a vector format. I realize we're going to be a little bit over time here, but I will very quickly run through the plot types. So there are 5. There's a very lovely plot types tab in the Matplotlib documentation where you can go straight to and just browse the different plot types and find whatever one that most closely matches the one that you need. And they're also grouped nicely. So the very basic pairwise plots are up here. There's one here that's not mentioned that's called a step. It's very similar to stairs, except you can control whether the centering of these the horizontal lines for the steps. Then there are these statistical distributions. A couple of these are very specialized. So event plots, I think, is only really used in neurology, but you can technically use it for something like a dateline. Then there's formats for gridded data like images and images, vector fields, wind barbs if you're a meteorologist, contours, field contours, those are separate. If you have irregularly gridded or unstructured data on an unstructured grid, then you can use these tri-contour, trip color, trip plot. Those basically connect your points as triangular meshes, and those are useful for those can be useful for networks, but I would still recommend using something like a network X if what you have is a true network and not something like just a triangular mesh. And then, of course, there's 3D and volumetric plots. And I'll go over, in the last lecture, I'll sort of go over the use cases and pros and cons of different types of these plots. So let me return to the presentation. This link is in the presentation. I can also copy it to the. I can also post it to the chat. But you can, if you still have the documentation open from the previous example, then you can easily navigate to it. I just want to make a quick note on the irregularly gridded data because this can be a little bit confusing. These are not meant for data that. If you're going to tri-contour or tri-contour F, they're not meant for contouring by point density. What they would contour by is the values of basically the Z values at each of these points. So each of these points would be associated with coordinates and then a value, a third value like a Z. And that's what's being contoured by tri-contour and tri-contour F. So if you want to contour by point density, what you want is a histogram or something called a kernel density estimation. And now, final example before we go to the break and then the first set of exercises. Okay. All right, so the solution to that is basically to rewrite your function like this. So you didn't actually have to change the name axes. I just do that to remind myself that these are different, that these are plural objects. So basically, all of the first figure I've assigned as axis 0, and I put these as 2 columns. You could have done 2 rows. That was fine. That would have been fine. And then for the MShow part, there's the value of Z, and then it's literally just image axes 1 dot MShow Z, and then I put the origin equals lower so that because the default is the way that Python arranges arrays normally sort of treats them like a table rather than an image. So you have to sort of flip it vertically. And then for the color bar, it's just plot.colorbar and then the name of the mappable, which I've assigned to image. All right. And any questions, any final questions before we go to the break?
Could you explain what was the 0 in the brackets for?
Over here?
Yeah.
So when you assign a plot.subplots and you give it and you tell it has more than 1 row or more than 1 column, then axes becomes an iterable. It becomes a container for multiple objects. So 0 means it's the plot on the left in this case, and the 1 means it's the plot on the right. If I'd given it two rows, it would have been 0 would have been the top and 1 would have been the bottom. If there were 4 subplots and there was arranged 2 by 2, then you would have actually needed 2 numbers here. So you would have had to have a row and a column specifier.
Okay, got it.
Any other questions?
So the exercise was to set it up that both are somehow equally square. Can we now even print out the size of axis of 0 and axis of 1? Is that possible?
When I said keep the plots roughly square, basically what I was saying was just set the figure size so that the aspect ratio keeps them close to square. There is a way to specify the plot sizes and more specifically, and there's also a way to control the aspect ratio relative between the 2 plots, so that you could say, you could actually shrink the left plot and expand the right one so that the image could be bigger and closer in size to its color bar and take up more than half of the figure. That's a little bit more complicated because it relies on subplot kwargs, which you have to which requires you to specify a dictionary. So if you go here, let's do subplot kwargs. So there's a whole lot of ways that you can do that. If you really want to control the relative sizes of figures, I would actually recommend the subplot mosaic if you want the images to be sort of integer sizes relative to each other. For these kind of things, then you can use subfigure. I haven't had to use a lot of I haven't had to do a lot of super fine-tuned resizing of things. So I couldn't really do that off the top of my head as a live demonstration, but there are certainly ways to control the sizes of subplots, both in the relative and absolute sense, more finely. Okay. All right, can everyone see the part 2 formatting and accessibility slide? You can just give a thumbs up or say yes. All right, cool. Okay, so this section and tomorrow morning we'll be focusing on sort of the global formatting constraints that are involved when you want to produce a figure for publication typically in the journals, in the journal format. So some of this will be about, controlling the layout and the appearance of certain aspects of your plot. And other parts will be about accessibility for some really common disabilities and other things that just help the reader or help the average reader and make the figures translate better to print, whether they're in color or black and white. Although I'm not sure that anybody actually still prints in black and white. Oh, there we go. So these are what I'm just for the time being calling the elements of plot accessibility. Your first priority ought to be clear and distinct data sets, but that very much depends on the plot type and the shape of your data. So for this section, we'll be focusing more on the other 3 aspects, which are fairly consistent across plot types. So the first thing you need is to make sure that all your labels are legible and they're correctly typeset so that they match what's in your text. Second is that you need to have your axes scales appropriately for the extent of your data. You need to figure out whether you need grids, and if so, what format works best for your data. And you need to have the ticks set up so that your data can be easily read if it doesn't make sense to include grids, or whether it makes sense to include grids or not. And lastly, you need suitable colors or color maps to make sure that your data are clear and distinct for every viewer, and not just the typical trichromat person. Well, so first, let's talk about the limitations imposed by figure size. The maximum figure size is basically determined by the journal's printable area. Even for online journals, they typically still stick with the original print format. And that means that your figures are constrained by the area within the margins. So the two main formats that they use are A4 and US letter, which typically have margins around an inch to an inch and a quarter, or maybe a little bit less for A4, which can have margins from like 2 to 3 centimeters. So the printable area is these dimensions, which don't mean a lot to you until you see the next figure on the next slide. So what this means is that you're limited in both the overall area of your figure and also the number of subfigures that you can include. So you have to remember about subfigures is that they also have to have labels, which means you're constrained on the size of the subfigure. You generally should not go below about an inch on a side, or even 3 centimeters on a side for a given subfigure. And also you have to remember that color bars, axis labels, and captions take up space as well. So typically you would only get in about, typically if you require more than 4 by 6 subplots, which works out to about 24 or 25, depending on the arrangement. If you need more than that, you're going to have to break it up somehow. So that's the limit on figure sizes. Now let's talk about typesetting. One thing that you need to know about typesetting for journals is that they usually require you to use something like LaTeX. Some journals accept Microsoft Word documents, but then you still have to know LaTeX, at least a little bit of LaTeX, in order to typeset your variables the same way on your plot in Matplotlib as there's typeset in your paper. And that's important. It's important that the symbols that you use in your paper in the article text match what's on your plot. And in order to do that, you need to know a little bit of basic LaTeX. So let's talk about that. LaTeX expressions, including just italicized variables, are bracketed by $2 signs, 2 US dollar signs. So for instance, if you're just writing like the sign of some angle A, then in order to typeset the A so that it's a variable and not some like extra text element, you need to use MathText and put it in these $2 signs. Most functions that modify characters in LaTeX have this syntax where you have a $, a backslash, the name of the function, a pair of curly braces, around the characters that are that the function is being applied to, and then the ending $. The exceptions to this are the superscript and subscript operators that they can work without they don't have a backslash, and they can work without the curly braces. But if you use them without the curly braces, they only apply to the first character that follows. So if you wanted to raise something to a power of 2, that's okay. You can do $2, and that's fine. But if you have if it's to a negative power, for instance, -2, then you would have to put -2 in curly braces, or else the minus sign will become a superscript, but the 2 will stay at the same level as the rest of the text, and it won't look right. There are also a lot of symbols that you can insert by name, but with a backslash and then the name of the character or the name of the symbol, like Greek letters, for instance. Most Greek letters you insert by putting $, backslash, the name of the Greek letter in English, spelled out in English, and then the other $. Also, conventionally, MathText letters indicate variables. So if you see a variable in italics, and also typically with serif font, those typically indicate variables. If you want to include something like a subscript, conventionally those do not get italicized. And so then you need to use this math remove function to unitalicize the letters in, for instance, superscript or subscript. There's plenty more documentation where that came from in Matplotlib's LaTeX documents. And there's also plenty of LaTeX or fuller LaTeX symbol indices that you can consult. There's a couple other things that you need to be aware of. If you're doing string insertion in a math text expression for like, for instance, if you're putting an equation with a variable coefficient that you calculated in your code, you have to know that string insertion creates a conflict between Matplotlib and LaTeX, because the curly braces are used for the format expression. So then the LaTeX has to be modified to accommodate this. And the way you do that is you have to double all of the associated curly braces that are associated with LaTeX commands. There are also a lot of Greek letters and certain symbols that require the input string to have this little lowercase r before the first quote mark. So like if you're inserting the letter beta, I don't think beta is actually one of the characters that requires this, but anyway, if you insert that, you have to put this R, quote, $, backslash, beta, $, end quote. That prints beta. There are also some operators with special meanings in LaTeX or Python. And if you want to include them as symbols in the text, as opposed to actually executing those functions, then for LaTeX commands, you need to include a single backslash. And for Python commands or Python operators, you would need to include a double backslash to make them render as text. And finally, spaces inside $signs are not rendered. So if you need to insert spaces inside of a MathTeX expression, you can use this backslash comma, backslash colon for a longer space, or backslash semicolon for a smaller space to insert them. So basically, these are 3 different spaces of different widths. And backslash exclamation point can remove unwanted extra space, like if you have a greater than or less than sign and then a number, and you want to render it as like less than 3 is one expression, and instead of having the full expression where the equal signs or inequality signs have spaces in before or after them. So this is an example of just how crazy this can get. So let's say this example, I typeset this VINIT with an over arrow, absolute value bars, and then the number, plus or minus, error margins, and then the units. This is the full expression. This up here with the R and then this really long line that trails almost off the edge of the slide. That's the full expression that you need to render this annotation here. And unfortunately, you cannot break these super long strings over multiple lines. Because, I mean, you can technically with a backslash, but it leaves the backslash in the output, which is annoying, but that's how it is. Anyway, so now you're going to give it a try with a very, very simple example. So in your return to the code that you use for the little codalon exercises in the first lecture. So what I want you to do is replace the A and B line labels with the math text typeset equations. And it's perfectly fine to use the inline fractions. There is a special way to use fractions in LaTeX, but I'm not going to go into it here. Now, for the image, I want you to label the horizontal axis alpha and the vertical axis delta. So the code that you needed was basically this. So you had to change the label R to cosine and then type the X with inside of the dollar signs. And then for the exponential curve, you had to remember the math remove for the E. Now, those were the tricks. The math remove for the E and the brackets around the exponential or the superscript expression. And for the Greek letters, since these were the lowercase versions, it was just backslash and then the word spelled out in all lowercase. If you want to type capital Greek letters, it's essentially the same command, except you capitalize the first letter. Just so you are aware for future reference. And these kinds of details are in the math text documentation. Now let's talk about axis ticks. The default is outward pointing ticks on the left and the bottom, but it's recommended that you add ticks on all sides for readability. It's up to you whether they point in or out, but the important thing is to be consistent. It actually used to be favored for all of them to point in so that the edges are nice and clean, but your data can actually obscure inward pointing ticks. So actually people are moving towards ticks all around the outside instead. So it's okay if your plot looks prickly. It's better that you can see where everything is, even if it's not the prettiest. If you want to add outward pointing ticks to the top and the right, there's this handy dandy tick params command that you will make extensive use of in the day 2 exercises. So you can do ax.tick parameters. This axis parameter lets you select X or Y, which refers to the major or minor axes. So when you put both, that means you're doing the X and the Y axes, and both for which means you're showing both the major and minor ticks. So the major ticks are the ones that are longer and typically have a numerical label attached, and the minor ticks are the short in-between ticks that don't typically have a label. There's top, bottom, left, and right quarks that are Boolean, and when you turn them on, so the bottom and left are true by default, but you can turn them off if the plot warrants it. But typically what you will want to do is just turn the top and right ones on. In that case, you just put top equals true and right equals true. And then you don't have to do anything for the bottom and the left because they're already on. Now, if you want to set the ticks inward all the way around, you can do, it's essentially the same command. The last command is the same, but then before that, you have to put axis.x-axis and then set tick parameters and then set the direction as inward. And there you can, and there the which controls the major and minor ticks. You can use both to turn them both inward, or I've never seen anyone do this, but you can actually select the major and minor ticks to point different directions. So for turning on the outward ticks, it's just one line. For turning on inward ticks all the way around, you have to turn the existing ticks inward before you can turn them all outward. And just remember, whatever you select, be consistent throughout your article. Consistency is always a good thing. Because when you're writing a paper, you build up, when a person reads your paper, you're building up expectations as you go along. So it's kind of, the tone is set by whatever figures come first, and then later figures, they're expecting sort of consistency. And that enhances readability. Now, usually the ticks are fine, but usually the built-in way of calculating where the ticks should go and what their labels should be. Normally those are fine, but you might need to modify them or manually set them if you want any of these. So if you want units with special formats or symbols like dates or fractions or currencies, if you want categorical variables like countries or months or species, or if you have if you want axis tick labels centered between major ticks, like for the, like if you're plotting bins, for instance. If you want secondary axes that are transformations of the primary axes, then you might have to twiddle with the ticks there too. Sometimes you do, sometimes you don't. If you want custom or power law axis scales, you will need to set those as a custom, with custom settings. And I honestly have never seen the use for power law axis scales. So you may need that, but I'm not going to address those. But also, you might need to modify your axis ticks if you have log or simlog or a sin h scaling with labels on every decade, and if you want visible minor ticks over more than 7 decades. Log and simlog, nonlinear scales can get tricky when you have too many decades, because then you really do need the minor axis ticks in order to, because the scaling is really not that as intuitive as a linear scale when you're just trying to read it off. So in these cases, you need to be able to learn how to control the tick labels and locators. And so here is an example where I mock up basically the point of this example is to show how you can do a secondary axis on the top, and how you can add, how you can force a log scale axis to print every decade instead of skipping decades, and printing minor axis ticks for a shorter number of intervals than you would normally see. And I'm showing these examples because these are ones that I encounter a lot, and the log locator function is not the most intuitive. It's one that gave me a lot of trouble to figure it out. So I'm hoping to spare you a little bit of the pain by giving people some heads up. So for the code at the right, the top part is just me setting up the function. You don't have to worry about it. The middle part here, do pay attention to this import matplotlib.ticker as ticks. So wherever you see me write ticks in the code, that's matplotlib.ticker. And then down here at the bottom, this is where I've defined the transformations for the secondary axes. So remember, when you're making a secondary axis, you have to supply both the forward and the reverse transformations. You don't have to supply them by name. You can give them lambda functions, but you do have to supply the forward first and then the reverse transformation second. So the top, or the first function is the conversion from the bottom axis to the top, and the second function is the top axis back to the bottom. And then for the tick locators, that's what's highlighted in these in this little green box here. So I've set the axis scales, and then I have to put set y-axis dot set major locator and dot y-axis set minor locator. So for each of these locator functions, you're going to have to pick out the axis first as an attribute of the axis object, and then you have to call a function off of that. So the set major and set minor locator functions. And then inside of these, that's where you set you invoke this matplotlib.ticker.log locator function. And for the major ticks, I set it as base 10, and then num ticks is not like, you don't have to pre-compute the total number. You just have to give it a number that's large enough to span the full axis. So you can give it an absurdly large number, but it just has to be larger than the number of major axis ticks that you expect to appear on that axis. So in this case, I already knew that the original data spanned about 12 orders of magnitude. So a safe bet is just like 99. It's large enough to be kind of absurd, but not so large that it imposes a computational burden. And the base 10 is what tells it that you want the major ticks to appear every decade and not like every other decade, for instance. Now for the minor ticks, this is a little bit trickier because similar rules apply, but now you have to use this subs quarg. And then you have to remember that the subscripts are only for the ticks that appear between the major ticks. They're not endpoint inclusive, basically. So for this, I wanted the minor ticks to appear every 2/10 of a decade. So I've included basically 0.2, 0.4, 0.6, and 0.8 as fractions of the span between the 2 decades. This is tricky stuff, and I will include the links to examples with the locator function in the exercises when you need it. And now here's another part. Once you set the major and minor locators, you need to set minor formatter and then use this matplotlib.ticker.null formatter. What this does is that it turns all the minor tick labels off. If you don't use this axis is just going to be a smear of text. You're not going to be able to read anything. So you need to include the ax dot whatever axis you're working on, and then dot set minor formatter, ticker dot null formatter. And now you can turn on the axis ticks all the way around. That's what this last line is doing. Okay, and this code right here, I'm not going to talk about it here. It was just an interesting way to indicate the visible part of the spectrum. It's in the documentation if you want to look at it, but I'm not going over it. A few final notes on ticks and tick locators. For color bars, there are ticks and format quargs in the color bar function. And the format quarg accepts all of the same locator functions as the ax dot x or y axis dot set major or minor locator. So it's essentially, it's pretty similar. Now, and also you should know that scales that are neither linear nor logarithmic are not suitable for histograms, contours, or image-like data. It just, histograms and contours cannot deal with nonlinear scales well. And histograms have the histogram functions have log scale settings, but that's all. Your scales are limited to linear and log. And contours, you can't really do log axes either. You kind of have to work in log units and then use the tick label formats to override those labels, to format them back as like powers of 10 instead of, you know, the log number. All right, now we're going to go to another code along. This is a really quick one. All you're going to have to do is call tick parameters and turn on the axis ticks all the way around for the left plot on your code along plot. So now let's talk about grids. These are nicely connected to the ticks. For non-Cartesian systems, you have to turn them on. People don't really think in non-Cartesian coordinate systems. However, typically for plots in Cartesian coordinates, they're discouraged. I personally am not fond of that fact, but it is what it is, and maybe it will change. It also kind of depends a lot on your plot and how precisely you need your readers to read it. But the Matplotlib defaults reflect the common preference for grids on for non-Cartesian systems and grids off for Cartesian. So for polar and axis 3D objects, there will be grids. There are also newer releases of Matplotlib that include projections.geo, and those support map projections like mole wide, hammer, and Lambert projections that are typical for Earth maps. And they're also customizable geo-axis base classes. However, the documentation on this in the Matplotlib documentation is not very good. So you'll have to find examples elsewhere on the internet. Matplotlib also accepts AstroPi world coordinate systems as axis transformations, and the documentation for that is on the AstroPi website. So it's not on Matplotlib, but at least for AstroPi, finding the documentation for how to use world coordinate systems in your axes, that is fairly well documented. The syntax for turning on a grid is actually fairly simple. It's just ax.grid and then parameters. You can use, if you want to turn all of the lines on as dotted lines and turn them silver and give them a line width of 2, that's what the code looks like. You can there's also usually an axis quad that lets you turn on like only the horizontal or only the vertical grid lines. And if you just want to turn on the default grid, it's just axis.grid parentheses. That's it. That'll give you a nice pale gray grid behind most of your data. It kind of depends on the plot whether the grid shows up behind or in front of your data, and also the order in which you turned it on. And so, but you can also assert the order of the grid with this Z order kwarg. So a lot of Matplotlib functions, not just grid, include a Z order kwarg that lets you tell Matplotlib what order to put things in. So if you want your grid behind your data, you set Z order equal to 0 to put it at the bottom. For scattered data, this is usually what you want unless your data are really, really dense and fill up most of the plotting area. Then you might want to put the grid in the front. But for image-like figures, you typically, for image-like figures, you can really only put the grid in the front. And you can use styles with light grids on a dark background if you have if you're using online figures. For online only figures. For print figures, you typically want to stay away from dark backgrounds and then light points, because that uses a lot of extra ink, and then you can be charged for that. That can cost you a lot of money. For lines, bars, stems, and those kinds of plots, you typically want a thin line and a neutral color set behind the data. And for bar and stem plots in particular, you typically only turn on the grid lines perpendicular to the bars. All right, so now what I want you to do is code along again, and you're going to return to your code and add this interpolation equals bicubic as a quark of ImShow. That will make the image a bit smoother so the grid lines show up better. And then I want you to turn on the grids for both plots. For the left plots, just leave it as the default. For the right-hand plot, the ImShow plot, I want you to turn on black dashed lines for the grids. To get these results, this was the extra code that you had to include. So on top of adding the interpolation bicubic to the ImShow plot, which was just literally just stuck this quark inside of those parentheses. For the left image, you just needed to click to select the correct axes and then click or enter dot grid. And for the right, you just needed to add dot grid, set the color equals to K, that's the single letter code for black, and then the line style or LS to 2 dashes. And I can show you with another, I can very briefly go over to the thin link, pause screen sharing, then go over to the thin link section and show you a couple of different ways to do this. I'm going to show you a couple of other, so that what you saw was bicubic. But the interpolation method of ImShow actually accepts any method that you can use for that SciPy interpolate accepts. So with a little bit of modification. So there's also like a spline 36, I think, or spline 16. Yeah. I changed the color map as well for this one. I'm going to remove these markers real quick and then turn this back to Veridis. So the default color map is that's that nice sort of yellow, green, blue map. That's called Veridis. And if I can also set the, come on. So if I wanted to do like a dash dot, for instance, then I could do something like this. Now that's kind of hard to see still, but then you can also adjust the line width with line width equals, let's say 2, just to be really garish about it. You don't actually want to do that because it's, you don't want the grid lines to, you generally don't want the grid lines to be more prominent than your data. You just want them to be visible if you have to include them. But yeah, this is what it would look like with the sort of customizing the line widths and line styles. For the first grid, I'm going to turn this, do this as show you what it looks like to just do the first axis. So let's say for some reason I only wanted to turn on the x-axis lines. Well, you just include axis equals, say, x. And that's what that looks like. Same thing for y. If I do this, Now it's only the horizontal ones.